I will start in a couple of minutes. I'll just wait 1, 2 more minutes and then I'll start. Okay, sure. So I'll share my slides now. Welcome everyone to the fourth live session of this course Structural Biology. In this live session, I'll be going through the main points discussed in the lectures of week 4, and we will end it by discussing some sample problems. So this week, we will go more into the depths of X-ray crystallography. I will revise what we just started in the previous class, is that how X-rays are produced. So there is an instrument called a X-ray tube where there are high-speed electrons which slowly lose their acceleration. So here you have a heat supply and a cathode that is heated. So the voltage that is passing through this wire is heating up this cathode filament. And when the filament is hot enough, it emits electrons. This is called thermionic emission. These electrons are then accelerated towards the anode. The anode is positively charged, which is why the electrons get accelerated towards it. And there is a high potential difference between these two, the cathode and the anode, of around 50 to 100 kilovolts. This anode, which is usually made of tungsten, is made very positive with respect to the cathode filament so that it attracts the negatively charged electrons and make them accelerate. Now, when these electrons hit the anode, the acceleration decreases, leading to a loss in kinetic energy, and it produces the X-rays. So once more, going through the entire process, uh, the electron beam is formed by heating up the cathode metal, which leads to emission of electrons. It is focused from the cathode to the anode. Often there are certain apparatus on either side of this beam, which causes the beam to be focused instead of spreading out. It's called the focusing cup. The distance between the filament and the X-ray tube target is around 1 centimeter, and in this short 1 centimeter distance, the potential difference is of 50 to 100 kilovolts. As it is being attracted towards the positively charged anode and thus accelerating, the velocity rises so much that initially what was zero, it becomes half the speed of light. So you can imagine how much acceleration there is. It's a huge amount of acceleration. Now, when this accelerating electron hits the anode, so this projectile electron interacts with the orbital electron of the target atom, that is the target atom in the anode. So the projectile electron is the electron that is being emitted from the cathode, and the electron in the atom of the anode is called the orbital electron. When this accelerating electron is hitting the electron in the atom of the anode, it results in loss of kinetic energy of this accelerating electron. And this kinetic energy is converted into thermal energy, heat, and electromagnetic energy in the form of IR radiation, almost 99%. And only 1% of this kinetic energy is converted into X-rays. So this is the basic instrumentation and method by which X-rays are produced. Now we'll quickly look into the electromagnetic spectra. As you know that radio waves have the longest wavelength of 10 to the power 3 to 10 to the power minus 1 meter. And energy is h nu, where nu is the frequency, or it can be written as h c by lambda, where c is the speed of light. So lesser the wavelength, greater is the energy. Radio waves have high wavelengths, so they are low energy waves. And from radio waves, as you go to microwave, infrared, visible, UV or ultraviolet, X-ray and gamma ray, from left to right, the wavelength is decreasing. That is, the energy is increasing. So X-rays are in the range of 10 to the power minus 8 to 10 to the power minus 11 meter, and they have high energy. As you can see, depending on the wavelength of the electromagnetic radiation, it can detect things of different size. So radio waves are large enough that they can only detect buildings, whereas X-rays are small enough that they can even detect the atom. So the wavelength that is typically used for XRD, stands for X-ray diffraction applications, are generally in the range of 0.05 to 0.25 nanometer, or if you want it in terms of angstrom, just multiply it by 10. So 0.5 to 2.5 angstrom. These are the wavelengths typically used in X-ray crystallography, and it helps you detect up to the atomic level resolution. So this is the entire electromagnetic spectra, and in X-ray crystallography, only waves in this range are important. Now there are two kinds of X-ray. There is something called continuous X-ray or Bremsstrahlung X-ray. So basically, if you have a fast moving electron, and so imagine this fast moving electron is from the cathode, and it passes through the electron of the anode. In the course of passing through the, it passes through the atom of the anode. So this thing is the atom of the anode, and the fast moving electron is ejected from the cathode by thermionic emission. While passing through this atom, it is repelled by the electrons of the atom, and this causes a loss of acceleration. So you can see that initially the path of the electron was straight like this, but due to loss of acceleration, the path of the electron changes as it moves through the atom of the anode. This loss of acceleration leads to the emission of energy in the form of X-rays, and these are called continuous X-rays because if you see this graph, on the y-axis it is the intensity, on the x-axis it is the energy. Continuous X-rays they don't have a specific energy. They have a range of energies. You can see this broad envelope that if you exclude these two sharp peaks, there is a broad envelope. And this broad envelope is what is the continuous X-ray or the Bremsstrahlung radiation, also called as braking radiation. This is formed when the electron moves through the atom of the anode, and there is a loss in acceleration of the electron, leading to release of radiation across a large spectrum of wavelengths, that is a large range of energies. So this Bremsstrahlung radiation or continuous X-rays represent a continuum. So you can see there is a large range of energy or a large range of wavelengths. So it is often called white radiation, because white light has light of all wavelengths, and Bremsstrahlung radiation has the uh, uh, has many different wavelengths in it. So it is often called white radiation. But the more important X-rays for us are the characteristic X-rays. In this, what happens is that, so this electron is the projectile electron from the cathode, and it collides with an electron in the atom of the anode. On colliding with this electron, if there is enough energy in the accelerating electron, it will knock out the electron of the anode. You can see this electron from the anode is just knocked out. This electron is knocked out here, and the projectile electron is also deflected. So imagine this is the electron 1, which is from the cathode. This is the electron 2, that is the anode. Electron 2 is knocked out from the atom, and electron 1 also gets deflected out. Now in space of electron 2, there is a hole. To fill up this hole, another electron from outer shell will move to the inner shell to fill up the hole. That can be from the L shell, that can be from the M shell. So from L it can come to K, or from M it can come to K. K is the inner shell. So when this is happening, this energy is fixed. Like energy difference between L and K shell is fixed. Again, energy difference between M and K shell is fixed. So when this happens, photons of a specific energy is released. So suppose it goes from M to K shell. It will give you a certain photon of h nu 1 of a particular frequency or wavelength only, because this is a quantized energy. Then if it goes from L to K, suppose this is h nu 2. So when this kind of X-ray is formed, where you have an electron from outer shell coming into the inner shell, then the energy that is formed is of a constant wavelength, because the energy difference between two shells is fixed. So in that case, you will get a sharp peak like this, which has one specific wavelength. So K alpha indicates the photon that is released when an electron transition happens from the L shell to the K shell. K beta is the X-ray that is formed when the electron transfer happens from the M shell to the K shell. These are all quantized energy levels, which is why when such a transition occurs, X-rays of only a particular wavelength are formed, and these are called characteristic X-rays because they only have a particular wavelength. Now, not every electron in each of the shell has the same energy. So in K shell, it has only one subshell, but L shell has three different subshells. So all electrons in the L shell do not have the same energy. There are three different energy levels within the L shell itself. And these are based, so this K, L, and M, it is determined by the principal quantum number n. In K shell, it is 1. In L shell, it is 2. In M shell, it is 3. Now, after the principal quantum number, there is something called the azimuthal quantum number or small l. When n is 1, L is 0. When n is 2, L is -1, 0, and 1. So L has 3 values, and so on. Now, so that is what it means, that not every electron in these shells have the same energy. So the shells are further divided. Now there is something called a selection rule, which says that delta small l, that is the change in the azimuthal quantum number, is plus minus 1. So from, you can see this radiation which is coming from, sorry, just 1 second. Let me just remove this. Yeah, so L value in K, it is just 0. In L, it is 0, 1, -1. And the selection rule is delta of the azimuthal quantum number L has to be plus minus 1. So the transition from 1 to 0, this is allowed because the L is changing from 1 to 0, delta L is 1. This transition is also allowed where it is coming from -1 to 0. So this is also allowed. But from 0 to 0, this transition is forbidden because delta L is 0, so it is not part of the selection rule. So the K shell vacancy can be filled by electron in the L shell, which comes from these two L levels, where the azimuthal quantum number is 1 or -1. Now, different metal provide different wavelength because different metals will have K, L shells of different energy. So, in different metals, this energy difference will be different, and so the energy of the X-ray produced will be different. That is, the wavelength of the X-ray produced is different. So depending on what wavelength X-ray we want, we need to change the composition of the anode. That is, what metal makes up the anode. And we must have a source of just 1 second. So we must have a source of monochromatic X-rays for X-ray diffraction. And meanwhile, since we only want X-rays of particular wavelengths, so here we saw that X-rays can be of two types: the continuous X-rays, which have a range of wavelengths, and the characteristic X-rays, which have very specific wavelengths. We want these specific wavelengths, K alpha and K beta. We don't want this entire range. So there are certain instruments which we can use to eliminate this entire range of emission that is happening, and it can filter out X-rays of specific wavelengths like the K alpha or K beta. Now there is something called the Bragg's law of diffraction. So imagine there are two crystal planes.
Excuse me, ma'am.
Yes.
Ma'am, am I the only one to join?
Yeah, actually, I think I started on time because like that was what we were told. But I can go through the previous slides if it will help. Will I do
Yeah,
that?
yes, ma'am. Yes, ma'am. Sure, ma'am.
Sure.
Thank you, ma'am.
So yeah, so this is actually a revision of the previous class only, where I was talking about how the X-ray is formed. So this I've already covered in the previous class. And this was also about the electromagnetic spectrum, and that X-rays are in the wavelength range of 10 to the power minus 8 to 10 to the power minus 11 nanometer. So this slide is actually new. So there are two kinds of X-rays. One is the continuous X-ray. How this is formed is that, so X-rays, you know that if the cathode is heated, electrons are produced from the cathode, and these electrons strike the anode and lose energy, which results in the formation of X-rays. So when the electron released from the cathode passes through the atom of the anode, the electron loses some acceleration. So the electron which was initially traveling along this direction gets deflected by around this much when it is traveling through the atom of the anode. So when this loss in acceleration is happening, the energy that is lost, the kinetic energy that is lost, is released in the form of X-rays. And these are continuous X-rays because they have a large range of possible wavelengths. So these are not of specific wavelengths. They can have a range of wavelengths, which is why it is called the continuous X-ray. And another name for that is the bremsstrahlung radiation. So in this graph, if you see, there is intensity on the y-axis and energy on the x-axis. So if you ignore these two peaks, the rest of the graph is a broad spectrum. So X-rays of all possible energies are being formed. So that is what is continuous X-ray. Now in characteristic X-ray, what happens is that the electron that is coming, it knocks out one of the electrons in the atom of the anode. So the electron in the atom of the anode moves out, leaving a hole here. In order to fill up this hole, one of the electrons from the outer shell drops into the inner shell. And this releases an, so suppose from the L shell, it can come to the K shell, or from the M shell, it can come to the K shell to fill up the hole that is left by the electron that is ejected. Now, when this happens, you know that the energy levels in an atom are quantized. That is, they have fixed energies. So energy difference between K and L is fixed, and that will lead to a characteristic X-ray, that is K alpha. Because the energy difference between K and L is fixed, you will get X-ray of only one possible wavelength. So energy of an X-ray is Hc by lambda. If your energy is getting fixed, lambda is also getting fixed. So K alpha wavelengths have only one particular wavelength. Another possibility is from the M shell, if it comes into the K shell, that also the energy difference is fixed. So that will lead to X-rays of another wavelength, that is the K beta wavelength. So since these are X-rays which have a particular quantized energy, that is, they have fixed wavelengths. So that is why these are called characteristic X-rays. Now, what this slide was saying is that not every I'll just remove these and I'll stop.
Ma'am, so what is the difference between continuous and
So you can see continuous. Continuous is this entire range of X-ray is continuous. If you leave the two, only this peak and this peak is characteristic X-ray. Everything else is continuous X-ray because there is a large range of possible energies and wavelengths. So continuous means that you will get a broad graph like this, and characteristic means you will only have certain peaks like this. Here it is kind of like it is shown on the same graph, but that is the difference.
But whenever the rays will pass, then the electrons will definitely move from ground state, state to excited state. So in
Uh,
continuous
hmm.
X-rays also, so the same thing is happening. Na? The electrons will move from ground state to excited state, and in characteristic X-ray also.
No, no. See, in continuous X-ray, the electron is entering and it is leaving from here, but none of the electrons in the atom are getting ejected. In characteristic X-ray, it is hitting one of, suppose this electron, it is hitting this electron and pushing it out of the atom. So the atom becomes a cation, it becomes positively charged, and there is a hole left here where this electron used to be. To fill up this hole, one of the electrons from the higher levels are moving to the inner level. In continuous X-ray, nothing of that sort is happening. The electron is coming from outside, it is just passing through the atom and getting deflected a little bit.
Is this possible? When we
Yes, it actually happens. See, I'll tell you when this happens. When your projectile electron does not have enough energy, so in order to knock out one electron from an atom, you need to have a certain level of energy. If your projectile electron does not have that much energy, it will just go through the atom and it will not affect the atom, but while passing through the atom, it will get little bit deflected. So at that time, continuous X-ray is formed. But if you provide high enough energy to the projectile electron, then it will definitely knock out one of the electrons in the atom, and then this characteristic X-ray will be formed. So depending on the energy of the projectile electron, you will either have continuous or characteristic X-ray.
Okay, ma'am. So why it is termed as braking radiation?
I
BRAKIN.
think it is just because acceleration is being lost. So imagine a car is going and you suddenly press the brake, so the it is kind of getting deflected. So that is why it is called braking. Just because acceleration is being lost, nothing else.
I mean the projectile electrons which we are providing here, their energy gets lost.
That
Means they
energy
are
is
their
released in the
acceleration.
form of X-rays.
Okay, ma'am.
Yeah. So another thing is that, as you know, uh, the K shell, L shell, they also have different subshells inside them. So from the K shell, so we saw that from L, if the electron is coming to K shell, we will call that a K alpha radiation. K alpha radiation can also be of different types because the L shell has different subshells. So there can be different wavelengths of K alpha, different wavelengths of K beta, and so on. Now, depending on what metal is being used, you will get a different wavelength because each metal also has very characteristic energy of of these levels. So, depending on what wavelength characteristic X-ray we want, we will choose the metal of the anode in such a way. And generally, for any X-ray crystallography experiments, we use monochromatic X-rays, meaning that we want only X-rays of one particular wavelength depending on our application. So any instrument, it will try to eliminate the white radiation. White radiation is basically this broad radiation. So the instrument will try to eliminate the broad radiation and filter out only the characteristic radiation, either K alpha or K beta, whichever we want. So that is just one of the characteristics of uh, how the of what is done before the experiment. Now I will go into this Bragg's law of X-ray diffraction. So this
Ma'am,
is
I can't understand that graph clearly. Means the
this
previous
graph
page,
is
the
oh
previous slide.
see imagine, so intensity is on the y-axis and energy is on the x-axis. So suppose you have only continuous X-ray, then you have a graph like this, where you have multiple X-rays of multiple energies and multiple intensities. So you have a range of X-rays that are being produced. This does not have much application because for application you need a monochromatic X-ray. Now suppose you have only characteristic X-ray. Then you will get a graph like this, where you are getting X-rays only at particular wavelengths, which are your characteristic X-ray. Now, sometimes both can happen at the same time, and this is that combined graph actually, where this broad envelope is also there and the characteristic X-ray is also there. So when this happens, you have to use an instrument to filter out you don't want this. You only want, say, this. So the instrument will filter out the other radiation. So you only get X-rays of one particular wavelength.
So how we will filter that?
Yeah, that is a like instrumentation part that is not there right now in the course. So yeah, that is not part of the course. That is like the instrument does it. So we don't need to go into the details of that. Do you have other questions?
No, ma'am.
Okay. So this was also covered, huh? Okay. So imagine that this is one layer of the crystal and this is another layer of the crystal, and the distance between the two layers is d. Now you have an incident beam of X-rays. In this beam, we are considering two rays, ray 1 and ray 2. Ray 1 is coming, hitting the top layer and getting diffracted. Ray 2 is passing through the top layer, hitting the bottom layer and getting diffracted. So there is a certain path difference between the two rays. So this path and this, so this area, this path that I've marked, this red line plus this red line, this is the extra distance that ray 2 is traveling compared to ray 1. And the measure of this, so this is the CB plus BD. So CB plus BD, that is this line segment plus this line segment, is the path difference between ray 1 and ray 2. Now, CB is equal to D sine theta. So D is this distance, theta is this angle. So if you see trigonometry wise, this is D sine theta, this is also D sine theta. So CB plus BD is 2D sine theta. Now, when this path difference is a multiple, is an integral multiple of wavelength, then there is constructive interference. So in constructive interference, what happens is that suppose you have two rays, the peak of the two ray and the trough of the two rays are in the same place. So then the amplitude of the waves will get doubled, and that is called constructive interference. In destructive interference, you have one ray going up, the other ray going down. So they will cancel each other out and the wave will be completely destroyed. That is your destructive interference. So what this equation is saying is that when the path difference between the two waves, the path difference we calculated was 2D sine theta. When this path difference is an integral multiple of lambda, like suppose you have one ray like this and another ray like this. So the path difference, sorry, just 1 second, let me, not like that. Yeah, so the path difference between these two waves is this distance, and this is lambda. Wavelength is basically the distance from the one peak. So this is the wavelength. So when the path difference between the two waves, 2D sine theta, is either lambda or it can be 2 lambda also. Imagine this extends by another lambda, this extends. So this will be 2 lambda plus lambda, 2 lambda. So when the path difference is an integral multiple of lambda, then there is constructive interference like this, and the net intensity of the wave will increase. So the Bragg's law of X-ray diffraction is basically this equation, which tells us that 2d sine theta, where d is the distance between the two crystal planes and theta is this angle, should be an integral multiple of the wavelength. This n is often called order of reflection. Now, according to, for some things that need to be maintained for this law to be true is that the incident beam and the diffracted beam has to be in the same plane. And the angle between the diffracted beam and the transmitted beam is usually around, so transmitted beam will basically be the beam that will pass through without any deviation. So the angle between this diffracted beam and the transmitted beam is usually around 2 theta. And we know sine theta cannot be more than 1. So this portion is less than 1. So, yeah, so since sine theta cannot be more than 1, so n lambda must be less than 2d. And so according to that, if we take n as 1, lambda must be less than 2d. So the wavelength of the characteristic X-ray that we choose should be less than twice this d spacing between the lattice planes. So that is how the wavelength should be chosen, that what wavelength we need to study what crystal. So first, the distance between the two planes of a lattice on the crystal is measured, and the wavelength should always be less than twice of that d. So that is the Bragg's law of X-ray diffraction.
Ma'am, but it can be equal to 2D also.
Yeah, it can be equal to 2D also if sine theta is 90, but generally sine theta 90 means that the ray will be like completely normal, right? So generally
Uh-huh.
that is not taken. So
Okay, ma'am. So what is this used for measuring that?
So normally we like what lambda we should use. So this lambda, what lambda we should take changes depending on what crystal we are studying. So in that crystal, the d is measured, and so this equation is basically what is important, that lambda is less than 2d. Lambda less than 2d. So suppose you have an unknown crystal. First, the d of the crystal is measured, and then we choose the lambda such that it is less than 2d, and then we get a good diffraction pattern.
Ma'am, and once you said that the ray one means, ma'am, actually distance traveled by ray
Sorry,
one.
your voice is breaking. Once more, can you say?
Yes, ma'am. Now, am I audible?
Yes, yes, you're audible.
Ma'am, actually, I was saying that once you said na that ray one and ray two means um, that d sine theta the length, sorry, d the
Haha,
length is
haha.
more in
This,
ray two than in ray one.
yeah, I said that the total distance traveled by ray 2 is greater than ray 1, and the difference in the distance is this d sine theta plus this d sine theta, these two extra.
Ma'am, so that the distance which is from that first atomic layer, that in
Hmm,
case of ray 2 till
hmm,
the point where both rays of ray 2 are meeting, means both rays
hmm.
of 2 are meeting.
Haha.
So that must be not the difference, that must be the difference between ray
Uh,
1 and ray 2.
no, no,
But
see,
here,
I understand your question. I'll just discard this and show you.
yes ma'am.
See, this is the entire length of ray 1. They have drawn a perpendicular on ray 2. So this length of ray 2, so you can understand this and this are equal, right?
Okay, ma'am.
And then,
Got it, ma'am. Got it.
so
Hmm.
like that.
Okay.
Okay. Now you know that crystals have a symmetry. So there are certain units in a crystal. The asymmetric unit is the smallest portion of a crystal in which you can carry out different symmetry operations to generate the unit cell. So unit cell, you know, is the smallest repeating unit of the crystal. So this is the unit cell. It is just shown by different patterns. So this unit cell, if you repeat it in 3 dimensions, you will get the crystal. But the asymmetric unit can be determined, can be just one arrow. Because if you turn this arrow by 180-degree, you will get the other region of the unit cell also. So the asymmetric unit is a part of the unit cell which can be either rotated or reflected to generate the entire unit cell. And unit cell is the building block of minimum volume, which has to be repeated in 3 dimensions to generate the entire crystal. And why it is necessary to know the symmetry of crystals is because if we know the symmetry of crystals, then it reduces the data collection by reducing the number of unique reflections to collect. So suppose you are trying to find the structure of a crystal, we can like first we can determine that what is the unit cell or what is the symmetry of the crystal, and then if we can determine the structure of a unit cell, then we can find out the structure of the entire crystal itself. That is why symmetry is very important, because if you can just understand the structure of the unit cell, then you can understand the structure of the entire crystal by repeating it in 3 dimensions. So that is the basic like things of a terminology in a crystal.
Ma'am, so in this case, uh, we must know the diamagnetic and paramagnetic substances.
Yeah, see, these arrows don't really represent diamagnetic or paramagnetic. They are just representing, so representing a particular portion of the crystal. It is being represented by arrow. So in reality, this can be a certain molecule in a certain orientation. And if you rotate the molecule by 180-degree, you can get the other part of the unit cell. So these arrows don't really have anything to do with diamagnetic or paramagnetic.
And what is said in the third point, the asymmetric unit is the smallest portion of a crystal structure.
So, say.
Ma'am, first it is saying that symmetricity
Again,
means.
your voice is breaking.
Ma'am, now am I audible?
Yes.
Ma'am, I was saying that in the second point, it is said that the symmetric means a single cell must be symmetric to be in means to be as a used as a repeating unit. And then
Right.
the next point, it is saying that the asymmetric unit is the smallest portion of a crystal structure.
Full line. It is the smallest portion of the crystal structure to which symmetry operations can be applied to generate the complete unit cell. So unit cell is independent on its own. You just repeat the unit cell in multiple directions, you will get the crystal. Asymmetric unit is a part of the unit cell which, if you carry out a symmetry operation, so if you carry out an inversion operation, so inversion means the top will go to the bottom and the bottom will go to the top. That is a inversion operation, also called a symmetry operation. If you carry out a symmetry operation of the asymmetric unit, you will generate the unit cell. So that is why it is called asymmetric unit, because it is asymmetric on its own, but if you carry out a symmetry operation, then it will generate the unit cell, which becomes the repeating unit of the entire crystal. So asymmetric unit is the smallest portion of a crystal structure to which symmetry operations can be applied to generate the complete unit cell.
Ma'am, concept is not getting clear yet.
Okay, so
Ma'am,
like
can you use some examples, or in Hindi can you?
um like I am also not that good in Hindi actually.
Ma'am,
Um
then with the help of an example, or you can explain in
um
Bengali too.
no, I am thinking like actually this class is more about the concepts, right? So I don't have any actual crystal example. I'm just trying to think like 1 second, huh? Let me just so
Okay.
suppose you have a unit cell where you have one atom here and one atom here, and this is repeating throughout your crystal. So this is your unit cell. The asymmetric unit is just this one atom, because if you reflect, so imagine there is a mirror here, mirror plane, and you're reflecting this atom to the other side, then you will have two atoms, and that is what forms your unit cell. So, and if you repeat this unit cell in 3 dimensions, you will get the crystal. So I will try in the next class to find a real example with real molecules, but right now the concept is this. So I think you will probably understand better if I put a real example, right?
Okay, ma'am. Ma'am, but next class definitely will you put
Ha.
this? Ma'am,
Yeah, yeah.
the class timing is same as today's timing, or it will be changed?
It is 6 to 8, Monday 6 to 8.
Ma'am, because I think previous week's class I was unable to attend. So actually,
No,
so many.
you
Uh,
attended, I think, right? You were asking questions and all. See,
that class only, or what, in which you were explaining about that I think X-ray diffraction only.
yeah, that was the previous class.
Okay, ma'am.
So I will take the class every Monday 6 to 8, and there is another TA who takes the class every Tuesday 6 to 8. So depending, same things are being taught. So whoever has Monday free can attend my class. Whoever has Tuesday free can attend that class.
Yes,
So
but I like your lectures more. So
okay, sure. So I will include this in the next class. I think better than qualitative like this, I think it will be better if I add a real example. So I'll do that.
okay, ma'am.
Okay,
Thank you. Mhm.
okay, right. So space lattice is an array of points in space such that every point has identical surroundings. So whichever point in the lattice you are choosing, the space should look identical from everywhere. So you can imagine any point in the lattice, if you choose, it will have similar surroundings compared to the other points. So that is what, so repeating units of the unit cell is forming your lattice. Space lattice and lattice is the same thing. So we will look at lattice first 1D, then 2D, then 3D. 1D lattice is very simple. You just have one point, and then after a distance of A, you have another point. Again, distance A, you have another point. And this goes to infinity in both directions. So 1D lattice has a single lattice parameter, that is this distance A. And you can get, so in 1D lattice, the mirror operator is same as, so after a few slides, I will be discussing these different symmetry operations. When this line will be a bit more clear, I will still explain it now. So imagine between two lattice points, you have a inversion point is basically, so this will be discussed again a few slides later. Suppose you have a line here, and this is an inversion point. Inversion point means you come to this line and you extend it equally in the opposite direction. And then if you meet a similar point here, then this will be your inversion point. This is not clear. I'll go to the example directly. Wait. Sorry. Okay. So you can see this as a molecule, imagine, and there are different groups A, B, C, and D. The center of this molecule is called center of symmetry or inversion point. So from A, if you go to the center and you move an equal distance in the opposite direction, you will get another A. If from B you go to the center and you move an equal distance in the opposite direction, you will get another B. Similarly, from C, come to the center and move equal distance in the opposite direction, you will come to C. So like that, from every atom, if you come to the inversion point and move an equal distance in the opposite direction, you will find the same atom. In that case, the molecule is said to have a center of symmetry or inversion center. Now, in case of the 1D lattice, we can imagine that between 2 points, there is a center of symmetry. Sorry. So between 2 points, there is a center of symmetry. Let's call it I. So if you move to the center of symmetry and move equal distance in the opposite direction, you will get another point. So again, here there is an I. You move to the center of symmetry, equal distance in opposite direction, you will get another point. So in one-dimensional lattice, there is a center of symmetry in between two lattice points. That is one symmetry operator. And the other symmetry operator is a rotation operator. Let's discuss that also. So rotational symmetry is basically, so imagine you have a axis passing through the center of the shape. Now, if you rotate from here, if you rotate to here, the shape is unchanged because this will come here, this will come here, and so on. But shape is unchanged. Then the molecule is said to have a rotational symmetry. In one-dimensional lattice, you can imagine an axis passing through the middle of 2 points. Now, if you rotate this point by 180 degree, this will come here, this point will come here. But the lattice will remain same. So at that case, it is said to have a 180-degree rotational symmetry. Because if you rotate along an axis passing through 2 points, the 2 points will just interchange their position. That is, the overall lattice will remain the same. So in between 2 points in the one-dimensional lattice, you have a rotational axis of symmetry, and you also have a inversion center, that is I. Because you can move from one point to I and then equal distance on the other side, and you will get the same point. So this is the symmetry involved with a one-dimensional lattice. Is that clear?
Yes, ma'am. The concepts are clear, but ma'am, I have a
Yeah.
question that in case of a chemical molecule, means like
Huh.
just like an amino acid, it is
Right,
always
right.
asked na, that whether it is chiral or not chiral, matlab a
Huh, huh.
chiral or chiral.
Right,
In
right, right.
that case, we see that plane of symmetry. So by
Hmm.
looking at that molecule, can we say that the molecule is chiral or not
Sorry,
chiral?
by looking, I heard
And
I heard up to by looking at the molecule.
means, ma'am, by looking at the molecule, can we say that the molecule is chiral or not chiral in spite of learning all the molecules?
Like it will be chiral only if there are four different groups attached to the molecule, right? Um, so like I'm not sure what your question is. Um, can you just clarify your question once?
Ma'am, like in that GATE exam, one question was there: is L-threonine a chiral molecule? Means true false was there, that which of the
Haha.
following
Hmm.
MCQs are correct? Which of the following options are
Right, right.
correct?
Haha.
So
Okay,
one
okay.
option was there: is L-threonine a chiral molecule? Then, in spite of learning that the molecules are chiral or not, by looking at that structure, can we say that the molecules are chiral or not?
So how
After
to?
means after different groups they have different groups, but uh, we will look at means L-threonine. I think L-threonine is a molecule of two carbons having different carboxylic acid and amine.
Correct.
But I was not actually at that moment clear about the structure. So uh, by looking at that is we will look at both alpha carbon and beta carbon, or we will only focus on the alpha carbon to see a molecule is chiral or not.
We generally focus on the alpha carbon only, like one second. L-threonine is basically your NH2, here is COH, and here it is OH. So this is your L-threonine. And for chirality, we generally see that center which has four different substituents, and that is only your alpha carbon. So any molecule which has any carbon which has four different substituents, you can call it a chiral center. And if a molecule has one chiral center, that entire molecule is chiral. If the molecule has multiple chiral centers, then in most of the cases the molecule is chiral. But in one case, this chirality gets cancelled out when, suppose, again, like, have you read about meso compounds?
uh, yes ma'am, but exactly means I can't
Yeah,
remember now.
yeah. Let me show. So if you have OH, OH, X, and just imagine this is Y. So this compound, this carbon is chiral. It is attached to four different groups. This carbon is also chiral. It is attached to four different groups. But there is a mirror plane of symmetry, because X and X is a reflection, OH is a reflection, Y and Y is also a reflection. So when there is a mirror, you have two chiral centers, but there is a mirror plane of symmetry, then the overall molecule becomes achiral. So this is an exception case. Otherwise, in any molecule, if you have one chiral center also, the entire molecule becomes chiral.
Means if one center is chiral, then the whole molecule is chiral. But if one
Hmm.
center is no, but no center is chiral, then the molecules is fully achiral.
Yes, correct. And
And
there is one exception case where you can have two chiral centers or more in a molecule, but if there is a plane of symmetry between the two chiral centers, then the whole molecule becomes achiral.
okay, ma'am. And if the plane of symmetry is not there, then the molecule is
Chiral. So suppose instead of X, this was A, some other, say this is some other group. Then there is no plane of symmetry and the molecule is chiral.
okay, ma'am. Means plane of symmetry leads to achiral, and if there is
Huh.
no plane of symmetry, then it's a chiral molecule.
Huh. And any molecule, it's a huge molecule, but it has one chiral center. Then your entire molecule becomes chiral.
Ma'am, can you please repeat it once? What?
So suppose you have a big molecule, and in
Mm.
that molecule, so imagine threonine only. In threonine, the beta carbon is achiral, it is CH3. COH is also achiral. But you have one chiral center, and that will make the entire molecule chiral.
Means you are talking about that this threonine part.
L-threonine, huh?
Okay. Okay, ma'am. Means OH position will not determine whether a
Yes,
molecule is
yes.
chiral or not.
Huh, huh.
Will it determine?
Only the alpha position. No, only the alpha position. Like if you're talking about amino acids, only the alpha position is important to determine whether the molecule is chiral or achiral. That is why in 20 of out of the 20 amino acids, 19 of them are chiral, because it is only glycine which has two
Mm-hmm.
hydrogens, and so that is not chiral.
Yes, ma'am. Yes, ma'am. Okay, ma'am. Got it.
Okay. Yeah. So we saw the 1D lattice. Now this is your 2D lattice. In 2D lattice, there are 3 lattice parameters. One is, so in 1D, it was only one dimension. In 2D, you have 2 dimensions along the x-axis and the y-axis. By lattice parameter, it means the dimensions of the unit cell. So imagine you have a rectangular 2D lattice. Then you have one length A, one length B, and you have the angle between A and B. So which is called alpha. So these are the 3 lattice parameters in any 2-dimensional lattice. Now, 2-dimensional lattice can be of different types. It can be square, it can be rectangle, it can be 120-degree rhombus or parallelogram. So in general, they have different properties. Like in square, both A and B are equal and the angle is also 90. In rectangle, A and B are unequal, but the angle is 90. In rhombus, you can see A and B, they are equal and the angle between them is 120. And parallelogram is general. It can be anything. So like it is the most general kind of 2-dimensional lattice. The actual lattices that are seen in nature are the 3-dimensional lattices. And these lattices have 6 lattice parameters. It will have, so it has the X, Y, Z axis. So this is a unit cell. The length along x-axis, we can call that A, y-axis B, z-axis C. And there will be 3 angles between each of the lengths, that is called alpha, beta, gamma. So in a 3-dimensional lattice, there are 6 lattice parameters, 3 distance parameters A, B, and C, and 3 angle parameters alpha, beta, and gamma. So to summarize, in 1D lattice, you have only one lattice parameter, that is A, that is the distance between the points. In 2D lattice, there are 3 lattice parameters, the distance along x-axis, distance along y-axis, and the angle between them. And in 3D lattice, there are 6 lattice parameters, 3 distance and 3 angle parameters. So now 3D lattice can be of 14 different types, which basically makes up the Bravais lattice. So in the Bravais lattice, the simplest one is simple cubic, where you have, one second, there should be another molecule here. So simple cubic is you have 8 molecules on the 8 corners of the cube. Body-centered cubic is, in addition to the simple cubic, you have one molecule in the center of the cube. And face-centered cubic is that in addition to the cubic, you have one molecule in the center of each face. So that is face-centered cubic. Now you can have different classifications, like you can have tetragonal, in which A and B lengths are equal. So X and Y axis length is equal, but Z axis length is different. So not equal to C. But all the angles alpha, beta, gamma are 90 degrees. So that forms tetragonal. Tetragonal can also be simple tetragonal, where you just have one atom on the side of each vertex, or body-centered tetragonal, where along with the simple tetragonal, you have one atom in the middle. Then you can have orthorhombic, where A, B, and C are all unequal. It may not be, in this diagram, it may not be very understandable, but at least this much is clear, that all 3 angles are 90 and all 3 sides are unequal. So again, you can have a simple one where only the atoms are in the vertex, a body-centered one where along with the simple you have one atom in the center, a base-centered one where you have the simple and only in the top and bottom face you have one atom in the center of the face, and a face-centered one where in all the 6 face centers you have an additional atom. Then in monoclinic, A, B, C are unequal and 2 of the angles are 90, but third angle is not 90. So slowly you can see symmetry is being lost. In cubic, all sides were equal and all angles were 90. In tetragonal, one side became unequal. In orthorhombic, all the sides became unequal. In monoclinic, all sides are also unequal and one angle is also not 90. So like that, slowly the symmetry is being lost. And then you have three special cases of rhombohedral, hexagonal, and triclinic. So triclinic is the least symmetric case where none of the sides are equal and none of the angles are 90 degree. So these 14, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. These 14 form the 14 Bravais lattices and they belong to 7 crystal system. So by crystal system, what they are saying is cubic is one crystal system. Within the cubic, you can have different types that they are not considering separately. Then tetragonal is another cubic system. Orthorhombic is another cubic system. So if you consider the, another crystal system. So if you consider the crystal system as the shape, like cubic, tetragonal, orthorhombic, monoclinic, rhombohedral, hexagonal, and triclinic, then there are 7 crystal systems. So overall in 3D lattices, you have 7 crystal systems and 14 Bravais lattices.
Ma'am, in the case of rhombohedral, the things are same as simple cubic, but the shape is a little bit different.
Yes, correct actually. Rhombohedral, if you only look at the unit cell, it is difficult to distinguish from cubic. But if you see the extended crystal, the packing is different. So that is how rhombohedral and simple cubic is being differentiated.
Okay.
Now we will look into the different symmetry operators. One is the mirror symmetry. So imagine, let's look at the X. So from the middle of the X, if you imagine a mirror, then one side of the X is reflection of the other side. Then it is said to have a mirror or reflection symmetry. Center of symmetry I just discussed little while ago. Then rotational symmetry also I discussed. Two others are there. One is translational symmetry. So if you move along a certain direction and the molecule gets replicated, that is called translational symmetry. This is this is observed in all lattice because lattice is formed like that only. You take one unit cell and you translate it in different directions to form the rest of the lattice. And glide symmetry is basically um, a combination of reflection and translation. So you first reflect this along this plane and then you translate it. Then the relation between these two is said to be, the relation between these two is said to be glide, which is reflection plus translational symmetry. Now there are often the symmetry can be represented by a matrix.
Ma'am,
So
what is the difference between that rotational and translational? Both are same rotation.
translation, you are just moving it, right? Rotation, you are rotating it along and see, you are rotating it. Imagine an axis passing through the plane of this slide. You are rotating it along the axis, right? Let me, wait, let me explain it. So, suppose you have something like this. Translational symmetry is just if you move it from one side to another, it is just, you are just moving it in this direction. Rotational symmetry is if you rotate it will become like this, then it will become like this, then it will become like this, then it will gain its original position. So you are rotating it along this direction. Translation is,
can we say
say,
that translation is 1D motion and rotation is 3D motion?
correct. 2D actually, you can say two-dimensional, right?
Okay.
Like if you look at this, you are rotating it in a two-dimensional direction, right? I mean, if the molecule is three-dimensional, then it will be three-dimensional rotation. Here the examples are 2D, so you can say that it is 2D.
In case of 3D, how we will do that translation? It will be the same as 1D or 2D translation.
In translation actually, so imagine
Like,
this unit cell here, right? If you move it up, it can be translation in the Z direction. If you move it to the side, it will be translation in the X direction. If you move it in this direction, it will be translation in the Y direction. So the unit cell has translational symmetry in all three directions, X, Y, and Z.
okay, ma'am, got it.
Now, often this symmetry operator can be represented by a matrix. So matrix multiplication, I won't go into that. You must have read that in mathematics. Now imagine you have this matrix and you are multiplying it with this matrix X, Y, Z. This matrix multiplication will give you the result matrix. X will become minus X, Y will become minus Y, and Z will remain as Z. This is equivalent to rotation along Z axis. Now imagine you have a molecule like this, and this is your Z axis. If you are rotating the molecule around this axis at 180 degree, then 4 and 6 will interchange places. 4 will come in the position of 6, 6 will come in the position of 4. Again, 3 and 5 will interchange places. So 1 and 2 are not affected because the axis is passing through here, but 3 and 5 and 4 and 6 exchange places. So that is that is basically 180 degree rotation along the Z axis. Now just 1 second. If you imagine let us look at the coordinates. So if coordinates of X 4, if it was X, Y, Z, new coordinates of 4 becomes X is minus X, Y is minus Y, and Z is unaffected. So that is how the coordinates of 4, 6, 3, and 5 are changing. X and Y coordinates become negative and Z coordinate is unchanged. That is why this matrix is called a 180 degree rotation matrix, because if you multiply this matrix with any three coordinates, it will change the sign of the X and Y coordinates, but the Z coordinate will remain same, which is what happens in case of a 180 degree rotation around the Z axis. Is this clear? You can ask if you have any questions here. Okay, so I'll move on. Now if you have, so this matrix was basically, you had minus 1. This is a unit, you can imagine, unit matrix is basically where you have 1 in the diagonal and you have 0 in all the other places. So in this matrix, you had minus 1 in X and Y and 1 in case of Z. That was your 180 degree rotation around the Z axis. Now, if you have minus 1 in all three, then all three will become negative. In the previous one, because in the row of Z, it was plus 1, Z remained as Z. Now, if you have minus 1 in all three, Z will also become minus Z. So, if the initial coordinates were X, Y, Z, after the symmetry operation, the coordinates will become minus X, minus Y, minus Z. This is basically what happens when you have a center of symmetry. So this CH3 group, imagine the coordinates are X, Y, Z. In center of symmetry, you will draw a line to the center of symmetry and an equal distance line in the opposite direction. So you will reach another CH3 group where the coordinates are -x, -y, -z. You can do this with any group. From N, you can reach another N. From CO, you can reach another CO. So any atom you take, if you take the negative of all the three coordinates, you will find the same atom on the opposite side. So the center of inversion can be represented by this matrix where the diagonal elements are all -1. Similarly, there can be other matrices to represent different operations. So we just saw the two-fold rotation, that is the 180-degree rotation along the z-axis is this matrix, where in the x row you have -1, in the y row you have -1, and in the z row you have 1. So this is what is said here. Two-fold rotation means 180-degree rotation. So the same thing is shown here. If you have three-fold rotation, see, these are more complicated cases. For the two-fold rotation and inversion, you can easily understand. But in the three-fold rotation or four-fold rotation, it might be a bit more difficult to understand. So what you can do is you can just remember, this matrix for the three-fold rotation, meaning 120-degree rotation. So imagine an ammonia molecule. You have the hydrogens in a pyramidal position. If you rotate this by 120 degrees, H1 comes here, H2 goes here, H3 remains, H3, so H1 goes here, H2 goes here, H3 comes here. So it is the same molecule. If you rotate again by 120 degree, you will get similar orientation. So that is what they are calling as three-fold rotation or 120-degree rotation. Four-fold rotation also, you can remember this matrix. Four-fold rotation basically means 90-degree rotation. So you have a planar molecule XCF4. If you rotate by 90 degree, F1 will go here, F2 will go here, F3 will come here, and F4 will go down. So that is a four-fold rotation or a 90-degree rotation. So in case of threefold and fourfold, it is a bit more difficult to understand the matrices. So we won't go into that. You can just learn, memorize that this is a threefold rotation matrix and this is a fourfold rotation matrix. So now we will look at reflection symmetry. Reflection symmetry is again easy. So in reflection, what happens is that, let us look at this molecule where you have carbon attached to two hydrogen and two chlorines. Now, if you consider a plane, one second, let me think how I'll draw this. This is a bit difficult to draw. Let me just, okay, so I'm thinking how to this. See, in reflection symmetry, what happens is that, suppose you are looking at, let us look at this case where you have one reflection plane. So in this reflection plane, what happens? If the coordinates of this was x, y, the coordinates of this become -x, y. And so when you are passing, reflecting along the y-axis, y coordinate,
Ma'am, you are saying the opposite. You Can you
Yeah,
do
you
that
can.
XY on this?
Yeah, I'll do that. If this is xy, this is minus xy. So if your reflection is along the y-axis, your y coordinate is same, x coordinate direction changes. So whichever axis you are taking for, here also the y coordinate, so this is x1y, this is x2y, this is minus x1y, and this is minus x2y. So this matrix basically stands for reflection along the, so here x and y are unchanged and z is changing. So if we imagine it in a 3D way, it will be, so let me go back to this molecule. Imagine you have a reflection plane along this. Then suppose this has xyz, xyz, xy will remain same, z will become minus z. So the z coordinate is becoming negative when you have reflection along the xy plane. That is what this matrix is showing. When you have reflection along the xy plane, your xy coordinate remains same, z coordinate becomes negative. So this matrix stands for reflection along the xy plane. Then you can have the translation operator. So translation, if it is along x direction, it will move in the x-axis. If it is in y or z, it will move around that axis. So for translation, no such matrix has been defined. But if you have glide symmetry, which is reflection plus translation. So if we go back to what was glide symmetry, you have a reflection operator followed by a translation operator. So for glide symmetry, you have, if you reflection operator along xy plane was where x and y remain the same, z becomes negative. So 1, 1, minus 1. This matrix is the reflection operator. And if you add, say, half, so this distance, the distance moved in this direction, if we consider it as half along the x direction, so if we consider this direction as the x direction, so the x coordinate is moving by half and y and z coordinate are unchanged. So you are adding reflection plus translation to give you the glide symmetry. For translation, you can add just this kind of a matrix will be good enough for translation. You don't have to multiply anything for the translation operator. You have to just do matrix addition. So that is how the glide symmetry is represented in terms of matrix operators. Now you can look at, so reflection versus inversion. You can see this two-dimensional structure of a rabbit. If it is reflected, it will appear like this. But inversion means that you have each point of the structure, you pass through the inversion point and you move an equal distance in the opposite direction. So that will generate the inverted image. So reflection and inversion are two very clearly different operators. And if you combine these operators, like glide was a combination of reflection plus translation. If you combine reflection plus inversion, you will get something called roto-inversion. So in case of, suppose you, when the roto-inversion axis is 1, that means there is no rotation. You are just inverting the, so the inversion center is here. You are inverting the molecule, passing it through the inversion center and moving an equal distance in the opposite direction. When the it is 2, then you are first rotating by 180 degree till the molecule comes here, and then you are inverting it. So you're passing it through the inversion center and an equal distance in the opposite direction. When it is 3, the rotation is through 120 degree. And after 120 degree rotation, it is inverted to get the roto-inversion symmetry with a n of 3. Similarly for 4 and so on. So roto-inversion is just a combination of rotation and inversion. Now we will just look into what are congruent figures. So congruent figures, two figures are congruent if they are the same size and the same shape. So the corresponding sides also have to be equal in length, and the angles also have to be equal in length. Only then you can call two figures to be congruent. So here you can see these two figures are congruent because the sides are of equal length in both, and corresponding angles are also equal. So, and then you can have different two congruent figures where one is translated or one is reflected and so on. So these are just different terminology that are being introduced in this set of lectures. And so you can see inversion leads to congruent images. So if you see inversion here, when this image was inverted, the resulting image and the original image are congruent because the sides are of equal length and all the angles are also equal. But when you have a three-dimensional figure like a chiral center, and in that you carry out a reflection operator, then you know that you get an enantiomer, that is, its non-superimposable mirror image. So these two are not congruent because congruent figures you can superimpose them. You imagine any of these two sets of congruent figures, if you bring them to the same orientation, they will superimpose. But in case of a three-dimensional chiral center, the mirror image is an enantiomer, so you cannot superimpose them. So they are two different molecules.
Ma'am, enantiomers are non-superimposable images.
Yes, that is what I was saying. So enantiomers are not superimposable. So enantiomers are not congruent, because congruent means you can superimpose them and they will have corresponding similar length of side and angles. So these are all congruent images. You can see, you can move them and bring them to the same orientation and they will superimpose. But enantiomers, no matter how much you move them, you cannot bring them into superimposition.
So that in the case of amino acids, we say that the molecule is non-superimposable or superimposable. This is on the basis of this thing only.
It is basis of chiral center. So if you have, so what I was saying that time, if you have even one chiral center in the molecule, the entire molecule becomes chiral. And whenever a molecule is chiral, its mirror. So that is like a rule. So in this carbon, you have 4 different groups attached to it. So this is a chiral carbon. And no matter, so in this entire molecule, you have only one chiral carbon, but that is enough to make the entire molecule chiral. And when a molecule is chiral,
this thing is on the basis of chiral, not on the basis of congruency.
That I was just saying that I was introducing the terms. Like if you have a question asking you plus lactic acid and minus lactic acid, are they congruent? The answer will be no, because congruent means they have to be superimposable. So I was just explaining the terms. I was not relating.
No, ma'am. My question is that in case of amino acids, the molecules are only chiral, not congruent.
Correct.
Means the structure is not congruent. It is always chiral or achiral.
Absolutely.
Congruency is never, means is not always, not always,
Yes,
but is never there.
Actually, yeah.
Yes. Okay. Ma'am, this portion is very much confusing. This is structure, symmetry, and all.
I understand it. So, one thing you can do is, again, the slides and lecture both will be uploaded. You go through it again slowly, and wherever you have questions, you send me in the mail.
Ma'am, is there any YouTube video? Means who are means in any YouTube link or anything from where we can see the structures also like 3D or 2D, and then they are explaining.
I have to check actually. I'm not sure. I will let you know if I find. You also search. I'll also see.
Ma'am, yeah, like when I saw sir's previous lectures,
Mhm.
sir was means with the help of 3D models and all, sir was explaining that I think in the first or second um, session, I think means after
Okay, okay.
first or second week, sir.
So you, okay,
Mhm.
okay. Huh. So you think it will be easier if 3D models are used to explain, right?
Yes, ma'am. Yes, ma'am.
Huh. I'll see if I can find any YouTube video. I'll send you the link, and otherwise I'll just show you with models in the next class.
Okay, ma'am.
Okay, so again, this is so we had combined rotation with inversion. We can also combine rotation with reflection. So this is a molecule attached to 4 different groups. You can rotate it through 90 degrees to get this orientation. And then if you reflect it, so this is your axis of rotation. And you are rotating it through 90 degrees along this axis. And then if you reflect it through the plane, you will get the original orientation back. So I think the first row might be a bit difficult to understand. So if you just look at the second row, that is same molecule seen from another orientation, which is one carbon attached to 4 different groups. So if you rotate it 90-degree through this axis, you will get a kind of orientation like this. And then if you reflect it through a plane which is perpendicular to this 90-degree axis of rotation, you will again get the same molecule back. So this is rotation plus reflection. It is often called improper rotation. So I think this also might be difficult to understand in 2D, right? So this also probably I'll find a video and I'll start the next class by playing the video so that this is clear. Because I think till single operation it was still understandable. Now it is combining 2 operations. It is a bit difficult to understand in 2D, right? So uh, leave this slide for now. I'll show a video explaining it properly at the beginning of the next class. Okay, now you can have different point groups to explain the symmetry of the molecule. So this again, we don't need to go into too much details of it because this is a very complicated topic. Um, we can there are different normally so a molecule can have different symmetry elements, right? Like rotation or reflection plane or center of symmetry or rotoinversion. So it can have different symmetry elements, and the combination of these different symmetry elements forms the point group. But we don't need to go into the details of this point group because as you can see, it is pretty complicated. So as long as we know the 14 Bravais lattices and the 7 crystal systems, and we know each of the symmetry operators separately, that is enough for this course. We don't need to go into how each of these point groups are named and all that. One more thing is that, so we have seen up to 4-fold axis of rotation, that is 90-degree axis of rotation. Normally we don't have 5 or 6-fold axis of rotation. To have a 5-fold axis of rotation, you need to have this kind of a pentagon structure. But if you have a pentagon structure, you can see crystal packing is not very good. You will have overlap in some places, you will have unfilled spaces. Compared to that, if you have square or triangle unit cells, they can pack very nicely without any overlap or unfilled spaces. So 5 or 6, like greater than fourfold axis of rotation does not occur in crystals. And another thing is the enzyme selectivity. So this enantiomers that happen, the non-superimposable mirror image, that is what leads to selectivity in enzymes. So in enzymes, you basically have certain active site, and the substrate molecule will come and sit in the active site, and the product will be formed. So enzymes are very specific to that particular substrate. It will not react with all substrates. So how can you make the enzyme specific to one particular substrate is by taking advantage of the chirality of the molecule. So suppose, so all amino acids in our body are L amino acids, right? So if we are taking a medicine which also has L amino acids, it will be able to interact with the amino acids in our body. But if you take a medicine which has D amino acids, it will not be able to interact with the amino acids in our body. So different enantiomers will react differently, and the placement of groups around the enantiomer is what leads to selectivity in enzymes. So that is another basic application of this chirality that is being just mentioned here.
Ma'am, so the enzymes is protein. That means it contains amino acids. So the amino acids are all of L mm, L system, or it can be D or L, but only where the enzyme is interacting, sorry, means substrate is interacting, only that portion will contain the L amino acids.
See, all naturally occurring enzymes are only L amino acids. Now, if you are artificially taking some drug which has a mixture of L and D amino acids, then only the L amino acids will be able to interact with substrate in the body.
No, ma'am. In the case of enzymes, means the enzymes which are present in our body, they only contain L amino acids, or some D
Yes,
amino
they
acids are also
no,
there.
they only contain L because they are the naturally occurring enzymes in our body. They will only contain L.
And can we provide artificial amino acids, sorry, artificial enzymes from outside?
Yes, that is what I'm saying, is that in some cases, like say some patients have some enzymes which is not being produced enough in their body, then they can take some artificial enzymes from outside. In that case, there can be a mixture of L and D, but only the L amino acids will be the ones that are interacting.
Okay, ma'am.
Then there is an instrumentation portion. These are basically for you to remember. There is not much to understand in these instrumentation portions, so I will just go through it. So the X-ray source, you can have a Crookes tube which looks, so the basic concept of all the three are the same. You have a cathode which is being heated to produce electrons, and these electrons are hitting the anode and producing the X-ray. So the basic concept is the same, but there are certain small differences in all. So in Crookes tube, what was there is that inside the tube, air was also present. So when your cathode is being heated up and the electrons are being produced, the electrons are hitting the air molecules, and like a lot of the electronic energy is lost by hitting the air molecules. So that it was not a very reliable source of X-ray. Then an improvement over this was the sealed tube, where vacuum pump was added to remove the air, and a vacuum was created inside so that whatever electrons are being produced, they can directly hit the anode. They won't lose any energy in hitting extra air molecules. And also this tube was cooled by, so there is a kind of jacket running around the system where water is passing through that jacket, because we saw that 99% of the kinetic energy is being transformed into heat and only 1% into X-ray. So 99%, so that much heat being produced, it will affect the instrument. So the jacket of water running around the instrument is cooling it down to avoid overheating of the target. And another improvement that happened is where rotating anodes were introduced. So the anode, instead of being stationary, it rotated. So what happened is that it allowed the heat to be spread out evenly over a large area. And also the electron beam, instead of being focused on one area of the anode, can sweep a larger area of the anode because it is rotating. So uh, that was the, so these are different in like basically the same instrument with small improvements and modifications. And you have a much more advanced instrument called a synchrotron, where you have large tubular rings under high vacuum, in which electrons or protons are moved at very high velocities. So these travel in straight lines until forced to turn a corner by powerful magnets. So these are different. So each of these gray units are different parts of this synchrotron. So when the particle is entering, it is traveling straight, but at the edges of these gray units, there are powerful magnets that causes the particle to turn. So instead of moving in a straight line, it is moving in a circular motion. And in order to like change the direction of these particles, there is a, so when you're deflecting the particle, there is an energy that is released that we get back in the form of electromagnetic radiation. So this is, so if you remember what happened in the continuous X-ray, the electron was coming, passing through the atom and getting deflected, and the loss in acceleration was obtained in the form of continuous X-rays. Synchrotron has a similar but much more advanced setup, where you have electrons or positrons moving, and at the end of each of these gray units, there are powerful magnets which constantly change the direction of the electron or positron. So it will speed it up to a high. So as the electron is moving, the more number of rotations it completes, the more the velocity of the electron. So ultimately, when the electron is moving out of this circle, it has a very high velocity. So synchrotrons are often called as particle accelerators. And then this high velocity electron can be used to generate X-rays. So it will become a very powerful source of X-rays, because the kinetic energy gained by the electron in moving around this synchrotron is very high. So the modern X-ray tube looks something like this. It is made of ceramic with a beryllium window. And there are labels about what anode or cathode type is used. And there is something called a collimator in all the modern devices. What it does is, so imagine the X-ray that is produced is like this, different rays in different directions. So many of the rays will cancel out, many will be deflected away. The collimator will force the rays to be focused in a narrow beam. So when you ultimately get the X-ray, you will get a narrow focused beam of X-ray, which will help you analyze the crystal much more accurately compared to if the beams were just scattered in different directions. So the instrument that is doing this, that is forcing the X-rays to become a narrow focused beam, is called the collimator. And you can have different filters that will, so a monochromator is a optical device that will transmit a mechanically selectable narrow band of wavelengths chosen from a wider range of wavelength. So what we saw in the characteristic and the breaking radiation was that you had a broad wave spectrum of wavelengths, and you only had certain characteristic wavelengths that you want. So using a monochromator, you can select particular wavelength that you want. So you can see this, the red line is where, so there are certain things called interference filter. So interference filter, what they do, so here you can see three types of wavelengths are there in the beginning: blue, green, and magenta. And the filter is allowing only the green wavelength to pass. So the interference filter helps to allow either a single wavelength or a small range of wavelength to pass through it. You can see here,
Monochromator is also known as polarizer, or they two are
yes,
different things.
yes, that is correct. Monochromator is also known as polarizer. That is why it is so, polarizer is generally better because um, monochromator generally it can partially polarize, it cannot fully polarize, but polarizers are much more accurate in that they will only allow one specific wavelength to pass through. But monochromator, it is less accurate because you can see this graph, the red line is where you have not used any filter, and the green line is where you have used filter. In the green line you also have other wavelengths, but the wavelength you want, that is k alpha, is the maximum. But that does not mean other wavelengths have been eliminated. The intensity of other wavelengths have been reduced. You can see k beta has been reduced, other extra radiations have been reduced, but it is not fully eliminated. But polarizers are much more accurate in the sense that polarizers will only allow a specific wavelength to pass through it. So yeah, interference filter is one kind of monochromator which uh, increases the intensity of the wavelength that you want and decreases the intensity of the other wavelengths. But the major drawback is that the background radiation is still high. You can see the background extra radiation is still, a lot of it is still there. And transmitted radiation is not very monochromatic. Monochromatic means single wavelength. But you can see there are other wavelengths also present. That is a drawback of the interference filter. Another thing you can have is a crystal monochromator, which can either be a flat crystal or a curved crystal. So in the crystal monochromator, you have a polychromatic ray hitting the crystal. Polychromatic means that there are many different present wavelengths present, and it is made up of, it is hitting the crystal monochromator, which is made up of suitable crystalline material positioned in the X-ray beam, so that the angle of reflecting plane satisfied the Bragg's equation for only one wavelength. So again, we don't need to look into how this is happening, but the crystal monochromator, what it does is that if you put a polychromatic X-ray, the result will be a monochromatic X-ray. It will be split up into the different wavelength components. And you can, the crystal can either be flat or it can be curved. So this is another kind of way in which the extra additional wavelengths are cut out and you only get the wavelength that you want. And so what has been done, the wavelength, firstly the X-ray was produced, then the X-ray was focused into a single beam, then all additional wavelengths were discarded and the wavelength that is of interest is being separated out. After that, you need to have the detector. So you can see here, the, just one second. Yeah, so you can see here the X-ray is being produced. Monochromator is separating out the particular wavelength you need, and then the X-ray is being made to fall on the crystal, and you have a crystal which is placed in a goniometer, which we discussed in the previous class, and then you have different diffraction patterns. So basically what happens, there is a film here, and the X-ray, when it passes through the crystal, it gets deflected when it hits the different atoms of the crystal. So the deflected X-ray will strike this detector and cause a dark spot wherever it is hitting. So there is an equation where the blackening of the developed film is expressed in terms of density units D, given by log I0 by I, where I0 is the intensity of the incident X-ray, I is the intensity of the transmitted X-ray, and D is the so whatever spot you are getting, they will have a certain density which is given by D. So this is like a photographic film. In a photographic film, whenever you expose it to light, you get certain, the photograph develops. Similarly, wherever the X-ray is hitting on this detector, you will get a certain pattern of spots. The disadvantage is that it is very time consuming and takes several hours. There are other methods of detection where you can have something called a Geiger-Müller tube, where you have a tube filled with inert gas, and the electron, after accelerating it, so inert gas like argon is filling the tube, and the accelerating electron is causing the ionization of the argon gas inside the tube, and the ionization is producing a lot of electrons that travel towards the anode, and this is detected in the form of electric signals. So this was a photographic method where you had a photographic plane, and wherever the deflected X-rays were hitting, you will get a dark spots. So that was like a photographic method. These are called a counter methods. So the basic concept of all these methods is that there is some gas which is there in the detector, and the gas is being ionized by the accelerating electrons, and there is some electrical signal. So instead of measuring it on a photographic plate, the detector is measuring it in the form of electrical signals. And of course you can have, so this is the basic schematic of the entire diffraction machine, where you have the X-ray tube which produces the X-ray. There is a focusing mirror, there is a place where the specimen is placed in the goniometer. The X-rays will hit the specimen, get diffracted, and then reach the detector. So this is the basic schematic of the entire X-ray instrument. And you can have coherent or incoherent light scattering. In coherent light scattering, the scattered wavelets have non-random relative phases. So you can see this is the incident wave, and in the scattered wave, all of them have the same phase. In the incoherent light scattering, the scattered waves, all of them have different phases. The path length is different. They are cancelling, they will interfere with each other in a destructive manner. So we are not interested in incoherent light scattering. We are mainly interested in the coherent light scattering, because they will interact in a constructive way and give light rise to better diffraction patterns. So that is what it is being said again about the coherent light scattering, is that the
Ma'am,
incoming,
when you will start the questions?
I think just some more. Yeah, I can start now, because the rest of the like information is kind of in the questions only. So I'll do that.
Okay.
So one question is that which metal is not used as a target anode in X-ray crystallography?
Iron.
No, it is actually zinc. So basically, for the requirement for the target is that it has to be metallic and it has to have a reasonably high melting point. So there are few metals which fall within it, is that chromium, iron, cobalt, copper, and molybdenum. So these five you can remember. Anodes are generally made out of these five materials. Zinc is not very good at conducting electrons because it has a completely filled d shell of electrons. So it is not very free to move around. So you just remember these five metals which are good to be used as anodes. The next question is that why copper anode is used in protein crystallography? So the answer for this is that copper, the K alpha wavelength matches the diffraction limit of about 2 to 3 angstrom for many of the protein crystals. So what is diffraction limit? Diffraction limit is the best possible resolution that you can get. So suppose if you get two peaks merged, which are fully merged or partially merged, this is not good resolution. If the peaks are clearly separate out like this, then it is very well resolved peaks, and this is what you want. Now the diffraction limit of protein crystals is 2 to 3 angstrom. Means that if it is 2 to 3 angstrom or a bit, it can resolve the atoms separately. Because we know that smaller wavelengths have better resolution power, and the K alpha wavelength of copper is around 1.54 angstrom, which is close to the diffraction limit of protein crystals. And that is why copper anode is used for protein crystallography. So the correct answer is A. This is just an information you have to remember. There is not like any explanation or anything. Another is that molybdenum, so copper anode is used for protein crystallography. Proteins are very large crystals. Molybdenum anode is used for small molecule crystallography. And why is that? That is because molybdenum produces X-rays with shorter wavelength. So if you compare here, the wavelength of molybdenum is the lower wavelength and the wavelength of copper is the higher wavelength. We know that to resolve small particles, we need smaller and smaller wavelengths. That is why for small molecule crystallography, molybdenum is preferred because you can see K alpha, K beta are both smaller wavelength compared to copper. And copper is used for large molecule crystallography, basically protein crystallography. Then you have a question, which of the following transitions are allowed? So here I will mention the selection rules for electronic transition. One I have already I think I discussed in the beginning, is that delta. So the quantum numbers are basically n, that is the principal quantum number, which is 1 for K shell, 2 for L shell, 3 for M shell, and so on. Then you have small l, that is the azimuthal quantum number. And azimuthal quantum number, if your n is 1, so azimuthal quantum number L is basically 0 to n minus 1. So if your n is 1, azimuthal quantum number is 0. If n is 2, azimuthal quantum number is 0 and then 1. If your n is 3, it is 0, 1, 2, and so on. And then you have something called J, that is the magnetic quantum number. And magnetic quantum number basically ranges from, you can see, it ranges from half, it can be 3 by 2, 5 by 2, and so on. So it starts from half, and then you can add it till it is uh, half, half plus 1, and so on. It will, so the selection rule which is to be remembered is this: delta n cannot be 0. So within the L shell, you cannot have transitions. Delta L is plus minus 1. That means, so L shell has 3 subshells. You can go from L1 to L0. So L1 you can go to L0. Again, L1 you can go to L0. But 0 to 0 is not allowed because delta L is plus minus 1. And delta J is plus minus 1 or 0. So these are basically selection rules that you have to remember. So if you look at option D, delta J, here delta J is 2. 5 by 2 minus half is 2. That is violating your selection rule. If you look at C, delta L for both these, delta L is 2. 3 minus 1, 2, or 3, 1 minus 3 minus 2. Either way, it is violating this selection
So
rule.
what should be the value of delta L?
Delta L should be plus minus 1. So it can go from, so look at this transition where it is going from 3 by 2, it is going from 1 to 0. So that is allowed. Or it is going from 2 to 1. So that is allowed. Delta L plus minus 1 is allowed. So this transition is allowed because delta L is plus minus 1. You just have to remember this selection rule. So the correct answer is A, because only in A you are following the selection rule that delta L is plus minus 1. Then you have a question that from which shell is the electron ejected in K beta X-ray? So let us look at the K beta. In K beta, electron is being knocked out from the K shell. That is why there is a transfer from M to K shell. So electron ejection happens from K shell. So the correct answer is A. And because this K shell electron leaves, there is a hole here which is being filled up by the M shell electron.
L cell electron.
See, it is K beta. So K beta is actually M to K is K beta. L to K is K alpha. You can see these two arrows are K alpha, that is L to K.
But K alpha is means subcell inside cell. K alpha, K beta stands for subcell of K.
No, like wait, 1 second, let me go back. Yeah, so see, when K alpha indicates the photon that is released from electron transition from L to K shell. So L to K is K alpha. M to K is K beta.
Okay, got it.
Okay. Okay. Then you have this question, smallest part of a crystal lattice that shows the three-dimensional structure of the entire crystal.
Unit
That
cell.
is your unit cell, correct. Then you have what type of lattice consists of one distance and zero angle parameter.
1D lattice.
Yes, correct. 1D lattice. Then this is a question, what is the unit cell of a 2D oblique lattice? This was not covered in the text. This is covered here. So 2D lattice can be square, rectangular, hexagonal, but there is also another kind called oblique where uh, the two sides are unequal and the angle is also not 90 degree. So that is option B. So like you are remembering the different Bravais lattices, you can also remember the different 2D lattices and the parameters. Then there is a question, how many angle lattice parameters are present in the 3D lattice?
3.
Yes. So 3 distance and 3 angle, and it's asking for angle, so it is 3. Now it is asking about Miller indices. So this I was covering in the slide. I'll explain Miller indices through this question. So for Miller indices, there are 4 steps. In the first step, you have to determine the intercept along x, y, and z axis. So the question is saying intercept of 4 along x, 2 along y, and 3 along z. So 4, 2, 3. The second step, you have to take the reciprocal. So 1 by 4, 1 by 2, 1 by 3. Third step, you have to multiply each of these by the least common denominator. So least common denominator of 4, 2, and 3 is 12. So if you multiply by 12, 1 by 4 into 12 is 3, 1 by 2 into 12 is 6, 1 by 3 into 12 is 4. And finally, you have to write the 3 numbers in a bracket without any comma, and that forms the Miller indices. So the Miller indices is 364, which is option A. So this is the general procedure of finding out Miller indices. Yeah, then this is asking how many Bravais lattices are there. So
14.
yeah, that answer is 14. You can remember each of them. And this is asking that what is the number of lattice points in a body-centered crystal system?
Body centered, there will be for 9, na? Means,
Uh,
but in body center, it will be only one in the body.
yeah, see, that is not the, see, the question is by number of lattice points, it means whole points. So you know in a cubic, at the corner, you only have 1/8 of an atom because it is sharing this atom with 8 other, like 7 other atoms. So the
Yes, ma'am, I got it. Got it,
so
ma'am.
1 by 8 into 8 is 1 plus 1 in the body is 2. So you will have total of 2 atoms, which is your option B. Okay, I think those are mostly the questions. And one question is there about just fourfold. So this was just asking that fourfold operation means how many degrees. So that is 90 degrees. So how to calculate the number of fold is that if someone is asking n fold means how many degrees, you just have to do 360 by n. So two-fold is 360 by 2, that is 180. Four-fold is 360 by 4, that is 90 degrees. So the option is B. So these are your, it's covering the concepts of this week 4. One thing I understood is that you are having some problems understanding the symmetry part. And for that, I will either you can put your email ID in the chat. So in the chat of the teams, you put your email ID, and I'll see if I can share some YouTube videos which will help you understand the symmetry better.
Ma'am, so here I will put in the chat box.
Ha ha ha. In
Okay.
the my Teams link, you just put in the chat. In this chat, you just put it. Yeah, okay. So these are all in small, right? You have put capital, but it is
Yes,
all
ma'am.
in small.
Ma'am,
Okay, fine.
Gmail, so
Ha ha.
we can write
Right.
in
Ha
capital or small.
ha ha.
Uh, and ma'am, what was your Gmail ID?
Oh, I'll give that
Forgot.
also again. Ha, you can send your questions here. Mine was ha, this one. Okay, then I'll end the class here. You can send me your doubts.
Ma'am, once
Ha ha.
you go to the slide, I have not
Oh,
taken
sorry,
any
sorry,
photo of
sorry, sorry.
email.
Ha. Yeah, yeah. Sorry, you're not seeing this. No, I stopped sharing. I'll share once more.
Yes, ma'am. Shreya B at the rate
Ha
IIST at the rate AC dot in, I think.
ha ha. You see, I've put the slide again.
Okay, ma'am. Okay, ma'am.
Okay, thank you.
Thank you so much, ma'am.
Sure, sure. Okay.